Okay, so first of all, we have to see waves क्या होती हैं. Waves is basically a disturbance created by a source in a medium. So we say it is disturbance generated by a vibrating or oscillating source in a medium. Okay, so basically wave is called disturbance. And if we look upon the sources of the waves, so we have already figured them out in the definition that the main sources are vibrating sources or oscillating sources. Vibrating source is one which by remaining on its position move to and fro. So these are the vibrating sources. And similarly, it can be oscillating sources. Oscillating sources are the one like the example is simple pendulum. So if we consider the simple pendulum example, the simple pendulum is moving freely between these two positions. So this is said to be oscillating sources. Okay, about the nature of the waves. Waves are used to transfer energy. So we say these are used to transfer energy from source to throughout the medium. Like they take the energy from the source and shift it throughout the medium. We are talking about medium, so we have to look at what is medium exactly. Medium is, let's say, a type of, it is a substance which can be solid, liquid, or gas, having particles used to transfer energy in the form of waves. So medium is basically solid, liquid, gas. Why? Because the atoms are there, and when you generate the disturbance, that disturbance is spread throughout that medium. The next thing is we have to look for the classification of waves. So waves are divided according to their features in several groups. The first group is based on material medium or simple medium, that all the waves in nature are divided into two groups. The first, according to their medium, so medium requirement. So the first group is called mechanical waves. And mechanical waves are the one which need medium to travel. Without medium, they cannot travel. So mechanical waves needs medium. And these are what? These are, let's say, water waves, sound waves. Okay, so these are mechanical waves. The second one are electromagnetic waves, EM waves. Electromagnetic waves are the one which don't need any medium to travel. Even if the medium is not there, they can transfer energy from one place to another. So don't need medium. Why? Because these waves consist of oscillating electric and magnetic fields, which is their medium. Oscillating electric and magnetic fields. And this is actually their medium. We say that this is their medium. They are carrying their medium with themselves. So examples are all electromagnetic waves. Read my inner values using X-ray glasses. So radio waves, micro, infrared, visible light, ultraviolet, X-rays, and gamma rays. These are all the examples of electromagnetic waves. So these don't need medium. So on the basis of the material medium, there are two types. First is mechanical waves, and second is electromagnetic waves. The next type is on the basis of vibration of particles. So the waves are divided into two groups according to the vibration of particles of the medium, or we can say displacement of vibrating particles of medium. Whenever wave is transferred through anything, through water, through air, through solid. Okay. Okay, so whenever the waves passes through a material medium, then it make the particles of that medium to oscillate. So there are two types of oscillation for the waves. On the basis of that, there are two types of waves. The first wave is called transverse waves. Okay, so the transverse waves are the one in which, let's say, if this is the medium, which is initially at rest, and this is the source which is going to move, vibrate, and produce the wave. Let's say it is moving, vibrating up and down. So then what's going to happen is that the wave is going to be moving this way towards right. So it means that the vibration of the source and the wave motion are perpendicular to each other. So such a wave is known as transverse wave. So we say that the source vibration, or we can say displacement of particles of medium. Same thing. Source of vibration or displacement of particles of medium is perpendicular to wave motion, or instead of that, you can say energy transfer. So the waves in which the source vibration is perpendicular to the wave motion are known as transverse waves. So they're called transverse waves. Okay, if we just look at the waveform of the transverse waves, we can say that suppose this is the rest particle of the rest position of the medium. So the wave generated in it will be in the form of crests and troughs. So the part of the wave that is above the mean position is called crest, and the part of the wave that is below the mean position is known as trough. And this dotted line is called rest position of medium. Rest position of medium. So this is the waveform of the transverse wave. Okay, in this, one thing is important, that source is moving up and down, and all the particles of the medium will also be moving up and down. That's why they are forming the crest and trough. So the crest means that the particles are above their rest position, and the trough means that particles are below their rest position. But the wave is going that way, and if you look at the oscillation of the particles, are like up or down. They can be up, they can be down. Later in this chapter, we will study that how which one of the particles are going up and which one of the particles are going down. This will be a separate topic. But at the moment, we are just representing that the source is moving up and down, so does the particles, but the wave is perpendicular to them. So this is the first type of the wave according to the displacement of the particle. Second one is, of course, longitudinal waves. Okay, the longitudinal wave is, you can say, opposite to that. So we can write down the definition on the same page as we have written for transfer. Let's say this is the source. Source can be anything. Let's say a loudspeaker. This is, let's say, a loudspeaker. If the loudspeaker is going to produce the sound, the loudspeaker will be moving back and forth. So when it will be moving back and forth, then it will be generating a sound wave which will be traveling like this. So this is compression, rarefaction, compression, rarefaction, compression. So the wave is also going that way. So it means that in the transfer wave, the wave motion and the source vibration both are parallel to each other. So we say that the wave in which source oscillation and wave motion are parallel is known as longitudinal waves. Longitudinal wave. Okay, so as in the transfer wave, there are crests and troughs. So here in the longitudinal wave, there are compressions and rarefaction. So these are the two examples of the waves according to their vibration or displacement of the particles. Okay, now we have to look for the third group. And the third group of the waves, the first group was the material medium. Like we categorize waves according to their medium. Some of them need medium mechanical waves and some of them don't need medium. So those are called electromagnetic waves. The second one was according to the vibration of the particles. So it was transfer waves and longitudinal waves. Now we have to look for the third one. And the third one is on the basis of energy transfer. We know that the basic primary job of the wave is to transfer energy, but there are some waves which do not transfer energy. And some of them, or majority of them, have transfer energy, but some of them don't. So the first type is progressive waves. Progressive waves. Progressive is originated from the word progress. So progress means that these are the waves which actually transfer energy throughout the medium. So we say that waves transferring energy throughout medium are known as progressive waves. And in fact, all the waves are progressive. So we say that all waves are progressive. Let's say water waves, let's say sound waves, let's say electromagnetic waves, etc. All these waves are progressive because all these waves use to transfer energy. But there are some other group of waves as well which don't transfer energy, and those are known as standing waves. Or sometimes we can say them as stationary waves. So as the name is suggesting, they are standing waves or stationary waves, so they're not used to transfer energy between different places. So the standing wave are the ones which don't transfer energy. So we say no transfer of energy due to permanent static points in waveforms. And those are known as nodes. Call them nodes. So due to these nodes, the wave doesn't transfer energy. So that's why we say that these are standing waves. Example, all progressive waves can be converted into standing waves. This is interesting. Into standing, like you can make standing wave of any wave. You can make standing wave of sound. You can make standing wave in water. You can make standing wave with light. You can make standing wave with a rope tied and moved in order to generate the waves. So these were the
are standing waves actually moving like in transfer wave or longitudinal?
Yeah, they are actually moving, but they are moving about their specific position up and down. They're not moving throughout the medium. So that's why we say that standing waves don't transfer energy, but they are used to convert energy from one form to another form. So their use is to convert energy between different forms. And these are mostly used in musical instruments. Musical instruments like flute or some other mouth organs are the instruments having long pipes through which they blow air and then the sound is produced. So in those musical instruments, standing waves are formed. Okay, now we have to look for important terms for the waves. Important terms. The first important term that we have to look is the displacement of the particle. So displacement, as we know that displacement is the shortest distance between two points. Okay, so I was telling you about the important terms, and the first important term that we have to look upon is the displacement of the particles. Displacement of the wave or displacement of the particles of the medium. So how we can define displacement? Let's first define that. Displacement is always the shortest distance between 2 points. So we say that the shortest distance of a particle or wave from its mean position is known as displacement. And if we talk about the symbol for displacement, the symbol for the displacement is often used as x or s, or yeah. And if we talk about its unit, so its SI unit is, we know it is meter, but mostly centimeter or millimeters are used. And if we talk about type of quantity, TOQ type of quantity, it is vector. Why? Because it is always away from mean. Displacement is always away from its mean position. Okay, so if I just draw a transfer wave and we can just see that, let's say this is a rope and it is fixed at the support, and then there are the, let's say, the particles marked as A, B, C, D, E. So these are the particles of this rope which are momentarily now at rest because there is no source. But right away, if we use a source and that source started moving upwards, then what's going to happen is, if the wave is moving up, if the source was here and the source was moving upward, so then this part of the wave will go up. It means particle A goes up, particle B stays over there, C, D, E, this stays over there. Now the source in the next step is going to come down. So let's say as you're oscillating the source, obviously it should be moving up and it should be coming down. Okay, so when it will be coming down, then this rope will be coming down as well, because first it went upward, then it went downwards. One is generated this and two is this. So it means that if the source is moving up, the rope or the medium attached to it will go up as well. And when it comes down, then the first part which was produced will start moving towards the right side. Now over here, there is no oscillation. Over here, there is quarter of oscillation. And this, there is half oscillation. Okay, now we have to complete one full oscillation. So for that, what we are going to do is just move the source again downwards. So this will be going up, this will be going down. And then as the source is going down, so then this will go down as well. Particle A is here, B is here, C is at the top, D is here, and E is here. Why? Because first the source went up, then it comes down. So 1 is this, 2 is this, and then 3 is this. Okay, and finally, because we are just trying to make one wave, and this is like 3/4 of oscillation, 3/4 of oscillation. And this is 4/4, or you can say one full, 4/4 or one full oscillation. So what's going to happen is that this will go up, this will go down, this will go down, and finally the last patch will be going up. So this was 1, this was 2, this was 3, and this was 4. So 1, 2, 3, and 4. So we say here one complete oscillation. So if one complete oscillation has happened, it means that over here one full wave has been produced. And how this happened, now we have to look for that. So this was the mean position, the dotted one. So you can see that initially the particle A was at the mean position, but when the source goes up, so the A goes to the highest point. So this is the displacement of A. Then this is B. So then highest is for B, and then highest is for C. So it means, and then finally here highest is for D. It means that inside a medium, when a wave is generated, all the particles of the medium will oscillate and they will reach their maximum point, which is called amplitude as well. Okay, so that's how a wave is being produced, and the displacement of all the particles are changing in a sequence. For number 2, which is very close to displacement, that is amplitude. Amplitude is written as x naught or A, and its SI unit is that of displacement. It can be meter, it can be centimeter, it can be millimeter. But what is amplitude exactly? So we say that this is the amplitude. So amplitude is the maximum possible displacement of a wave from its mean position. So the maximum possible displacement of a wave or a particle, it can be wave, it can be particle, from its mean position is known as amplitude. So in other words, we can say that amplitude is actually the maximum displacement gained by a wave. And if we want to calculate or measure or draw the amplitude, let's say I have drawn a sinusoidal wave, and let's say this was the mean position. So this is called mean position. So the amplitude would be the longest distance from mean to extreme, or it can be the longest distance from mean to the bottom extreme or the crest. So that is amplitude. Number 3 is time period. Okay, time period is denoted by T. Yeah.
What's the difference between displacement and amplitude?
Okay, displacement and amplitude. Displacement is the basic feature. It is the shortest distance of a particle or wave from its mean position. And this cannot be maximum. It can be maximum, but this is just generally wherever the particle reaches, you have to see that how far is it from its mean position. But the amplitude is the maximum displacement. As I've written, maximum possible displacement. So amplitude, you can say, is a type of displacement, but amplitude is always maximum. It can never be less than that, right? Okay. So the next thing that we have to look upon is time period. Time period is defined in a number of ways. If we define through source, we say that time taken by source to complete one oscillation. That is called time period. Like it's actually the time taken by the source to complete one oscillation. Or we can have another definition as well. That is time required to produce one complete wave. This is regarding source. That the source which is producing waves, of course, that source is taking some time. So we say that the time taken to produce one complete wave, only one wave. It can be compression or expansion, expansion, or it can be crest or trough. So time required to produce this is called time period. If we talk about the equation, so the first general equation is time period is total time over number of waves. So this was the first official equation to find the time period. If you know the total time, you just divide that by the total number of waves, so you can find that. The next one is in terms of frequency. T is equal to 1 over frequency, where f is the frequency and it is in hertz. Okay, now we have to look for one more thing, which is wavelength. And wavelength is denoted by the symbol lambda. So in the O levels, you must have read that it is the distance between two crests or distance between two troughs. Okay, that is fine, but here we'll be writing something else. So we'll be writing the straight line. I guess I have to correct the spellings. The straight line distance between two in phase means identical, 100% identical. So the straight line distance between two in phase points on a wave is known as its wavelength. So it's actually the straight line distance between two in phase, and I have to write something more as well, two in phase adjacent points. This is important. Adjacent means they must be very close together. So let's say, again, I have to make a wave. So I'll try to make again a wave. And then this is the center point for that wave. So of course, this is crest, this is trough, crest, trough, crest, trough, and crest. So the first thing that we know, it is the distance between two in phase. So in phase is always crest and crest. And it is always trough and trough. Or it can be the point on the mean line, which are lambda apart, like crest and trough are there. So these points and many other points can be known as in phase and distance between them. But distance between the adjacent one, the closest ones, are called the wavelength. In order to get the equation of the wavelength, we have again several methods. The first one is ratio method. So for the ratio method, lambda is equal to total. Okay, beta. So we were looking at wavelength. So wavelength is, as we have already written, that wavelength is the distance between two identical in phase closest points. So we say distance between two adjacent mean closest in phase. In phase means similar points is known as wavelength. So what are the points that are adjacent and in phase? So on a waveform, I have drawn a waveform, so we can say, okay, the crests are the one which are identical points. So these are the crests. So what are the crests that are closest? So these two crests are closest. So we say that the distance between the closest or adjacent identical point is called wavelength. In the similar way, these are the troughs, but we have to look for the adjacent one, the closest one. So these two are the closest one, so distance between them is equal to lambda. In the similar way, there can be many other points. Let's say if I take one point, this, where wave is going up, then from here the wave is going down, and then at this point again the wave is going up. So these 2 points are again adjacent closest points. So the distance between these 2 points is called lambda. So there are 3 ways. One is crest and crest, other one is trough and trough, or other one is one crest plus one trough. So all of these makes a distance equal to lambda. This is, I mean, the common thing from O levels as well. If we talk about half lambda, so that is like length of one crest or one trough, that is equal to half lambda. So let's say if this is one crest or if this is one trough, so their length is equal to lambda by 2. So this is lambda by 2 or this is lambda by 2. Similarly, lambda by 4 can be half of crest or trough. So let's say if this is one full crest or this is one full trough, so what we do is if we take half of the distance of the crest, that will be lambda by 4. If we take half of the distance of the trough, that will be equal to lambda by 4. So the equations to find wavelength, the first equation is wavelength is equal to wave speed over frequency. If you know wave speed, that will be in meter per second or any other unit, and then this is frequency. So dividing them, you can get wavelength. The other one is total length over number of waves. L is total length and N is number of waves. So doing this, you can find the wavelength. This will be usually used for the waveforms when too many waves are given. So then you will be using this formula to find the wavelength. And this formula, of course, when you will be given with the wave speed or wave frequency, then you would be able to use this formula. The next term that we have to look is speed of wave. Speed of wave, it is V. So speed of wave means the distance moved by wave per unit time. So as we know that wave transfer energy and wave moves from one place to another place. So it is actually, speed of wave is actually the distance moved by the wave per unit time. So we can define it as distance moved by wave per unit time is known as wave speed. Talking about its equation, so we have a standard wave equation, which is V equal F lambda. And its derivation is also there in IGCSE. But if we derive it here, we can say that, let's say this is a source which is completing one oscillation, like one movement up and down. And in the meanwhile, it has formed one complete wave. So let's say it has formed one complete wave. So this is crest and this is trough. So one complete wave has formed. So we know that in the one wave, how much distance the wave have moved, that is equal to lambda. And as it is one wave, so how much time it takes to produce one wave, that is called time period. So this is time period and this is wavelength. So we say, okay, we know equation about speed, that is distance over time. And how much distance the wave has moved when one wave is formed, it is lambda. And how much time t? So we'll say, okay, replace these values over there. So at place of d, we can write lambda. At place of t, we can small t, we can write capital T. So we can further just rearrange it like this, 1 over t into lambda. And you know that 1 over lambda is always equal to frequency. So that's how we can initiate this, that v is equal to f lambda. So these are the simple derivations for this. Okay, now let's look upon few examples. For all electromagnetic waves, we will study them later as well, but their speed is 3.0 into 10 to the power 8 meter per second, and usually it is not mentioned in the question. Why? Because we should know that the speed of the electromagnetic wave is 3 into 10 to the power 8 meter per second. So that's why they will not mention this speed. Instead, they will just tell us about frequency or wavelength, and they will ask us to find the other thing. Let's say if they can ask us, okay, red color, if there is red color, and red color wavelength is 700 nanometer. So they can ask us that, okay, find its frequency. Or in another example, they can ask us that the radio waves have a frequency of about, or not radio waves, let's say ultrasound. So ultrasounds have a frequency of, let's say, 25,000 hertz, and the speed in air is 340 meter per second. Or we can use the speed in the, let's say, the water, 1500 meter per second. So find the frequency. So look, if they have given the red color, they have not given us the speed. But if they have given us the sound waves, then they have talked about the speed. Why? Because the speed of the sound wave is different in different medium. That's why they will give you the speed. But for light or electromagnetic waves, they will not tell you about any speed. So you'll be saying, for one, we'll be saying that we know that v is equal to f lambda. You have to find f. So make f as the subject. So this will be v over lambda. We already know it is the fact that the speed of all the electromagnetic radiations or white light or even color of the white light, they have the same speed of 3 times per 8. And then wavelength is 700, but the nano is over there. So you have to be careful with that. Nano is minus 9. So you will solve this and you will get the answer in hertz. For the second one, again, it's simple. The speed is already given to you, which is 1500, and the in this one you have to find the wavelength, not frequency. So you'll have to find the wavelength. So we'll be saying that, okay, you have to make lambda as the subject. So lambda would be v over f. So f is 25,000. So you will simply divide them to get the answer of the wavelength. I mean, v equals f lambda is quite simple to apply. Okay, after this, there is another term which is called wave front. Let me tell you about that as well. Wave front. What is wave front? We know that if we talk about water waves in ripple tank is a lab device. It is a small glass tray in which we can produce water waves and we can investigate their properties such as reflection, refraction, and diffraction. So let's say the waves are there in the ripple tank, and these waves are as water waves. So the waves are moving like this, and there are too many waves which are being produced inside the tank, and all waves are moving like this. Okay, so as all the waves are moving in this direction, but what we can do is we can have these crests. So all these crests are on top of each other, so we can just join these crests together. Similarly, if we join the crest, then we have to join all other crests as well. But if we join troughs, then we can only join all troughs. We cannot join both the crest and troughs simultaneously. So now I have drawn these three parallel lines. So instead of drawing the blue waves, I can just draw these three lines, and I can tell that the wave motion is in this direction, which is perpendicular to these lines. So this red line is the wave motion or energy transfer, like energy is being transferring towards your right side. And what are these? These lines are called wave fronts. These are wave fronts, and two wave fronts or two lines are lambda apart. So it means that these are the wave fronts, the plane lines, which are used to represent the wave motion. So we say that wave fronts are imaginary lines used to represent wave motion. Okay, if we talk about their types, so there are two types. The first one is plane wave fronts, the one I have made, plane wave fronts. And the second one are circular wave fronts, circular or spherical wave fronts. Okay, so what is common in these two? Like, what are their common features, like common features of the wave fronts? The first common feature is that distance between two adjacent wave front is lambda. Distance between two adjacent wave fronts is equal to lambda. And the second feature is wave fronts are always perpendicular to wave motion. Wave fronts are always perpendicular to wave motion, like the way I have drawn over there. So these were the plane wave fronts. Okay, so these were the plane wave fronts. So let me draw the spherical wave fronts now. For spherical wave fronts, they will be in the form of the circles, equidistant circles, like this. Okay, what do they represent? They represent actually the wave originating, like if this wave is crest, so then crest and crest. So if this is crest, then crest and crest. Like all these are formed by joining the crests together. Crest, crest, and crest. So it means that actually the waves are going from the center, the wave is being produced, and they are going outward like this. So the waves are spreading in all these directions. So the blue circles are called the wave fronts. These are the circular wave fronts. And this black one is the wave motion, like wave is going in this direction. And the same thing is that the distance between two circles is wavelength, just similar to the plane wave front. So they have all the same properties as that of the plane wave fronts, except for the thing that they are in a circle. Okay, so after this, we have to go for another important aspect of waves, that is particle of medium features. And in the features, we'll be looking upon their direction of oscillation, their speed, their displacement, etc. So particle of the medium. We know that the mechanical waves need medium to travel. So in this aspect, we're talking about water waves. So when the wave is going in the water, so water particles are moving up and down. If the wave is in the rope particles are moving up and down. If the wave is in the sound, then the air particles are vibrating. So and if electromagnetic, then of course electromagnetic waves don't need any medium because they have their own medium with themselves. So I'm just talking about the mechanical waves. So let me tell you an example. For example, if this is water surface, and water surface right now is at rest. It means that there is no disturbance or there is no wave in it. And let's suppose that there are too many particles. There are like billions of particles, maybe many times more than billions of particles, but I'm just drawing few of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these 10 are the particles. So I have drawn 10 particles of the medium, and all these particles are at the mean position. So this is called mean position or rest position. Like this is the position when there is no wave, so the particles stay on their position. Okay, now what happened is that if we generate a disturbance, let's say a source was there, let's say this was the source, and we repeatedly move it up and down, up and down. So what happened is that after some time, all these particles would start moving up and down. So let's say all these particles started moving up and down, and like this. So a wave is being produced over there, and that wave is going this way. Now, what happened to those particles which were at rest? So this particle 1, let's say, was here. Particle 2, let's say here. Particle 3 is here. Particle 4 comes here. Particle 5 is here. 6 comes here. 7 here. 8 is here. 9 is here. And 10 is here. So these are the particles. I have just drawn them at their actual position where they are, like this. Okay. So these are the particles' position. The particles are displaced now to the new position. So all the particles are displaced from their position. So their displacement changes, their speed changes, their direction of motion changes. So now we have to look upon them. So first of all, if we talk about displacement, so that is simply the distance from their mean position from this red line. So we have already learned this thing in the previous class about the displacement and amplitude thing. Displacement can have any value, but the amplitude is the maximum displacement actually. Amplitude is maximum displacement. So all the particles have their different displacements. The one at mean and the one at extreme. If we just discuss them, so the ones they are at mean, their displacement is 0, and the one they are at extreme, their displacement is maximum, that is equal to amplitude. And one more thing, that this displacement keep on changing. As the wave is moving, the displacement of the particles keep on changing. They will never remain the same. Particle 1 displacement is 0 at the moment, but at the moment it is 0. Next moment it will increase. Particle 2 is having the maximum displacement, which is amplitude, but this is not permanent. This is temporarily. So after some time, particle 2 displacement is going to decrease. Particle 3, maybe its displacement will increase. Particle 4 will increase. Particle 5 will decrease. It means that all the particles will be having their displacement between 0 and maximum. So we can write that all particles, which I have labeled 1 to 10, will have displacement x greater than or equal to 0, and then less than or equal to the amplitude. A is amplitude. So this is the expression that the displacement will be between these two values. It is not fixed. The next thing that we have to look upon is speed of particles. So the speed of the particles will be like the ones which are at mean, the one which are at mean and the one which are at extreme. So the particles which are passing through mean, they have maximum speed. And the particles which are at extreme, they have 0 or minimum speed because they are momentarily at rest. So whenever particle passes through mean, its speed is maximum. And whenever it reaches at extreme means rest or trough, its speed is 0. So let's say if I quickly draw a wave like this, and this is the mean position. So we can say that the particles at extreme, here their speed is 0. And if the particle is at mean over here, over here, over here, or over here, their speed is maximum. So the particles at mean, they have maximum speed. Okay, the next thing is the movement, the kinetic energy. So kinetic energy, we know that kinetic energy proportional to speed square, so it will be the same. So kinetic energy will be max at mean position, and the kinetic energy will be minimum at extreme position. Then the potential energy. Potential energy is proportional to displacement of the particle. We know that potential energy is the change in energy due to change in position. So we say that if the particle is at mean, then its potential energy is 0. And if the particle is at extreme, it is having maximum displacement, so its potential energy will be maximum. So it means that we came to know one thing. For the kinetic energy, it is maximum at mean position, but for potential energy, it is maximum at extreme position. Okay, now is the most important thing, the instantaneous position. Instantaneous position of vibrating or oscillating particles of the medium. So again, as the topic is of waves, so we'll have to draw many waves. So let me draw a simple transverse wave. The crest and troughs are always equal. It's just because of the freehand drawing. Maybe it seems that some crest is bigger than the trough, but that is only due to the manual drawing. Otherwise, they're always equal. So let me carefully sketch it again. So let's say this central line is the mean line. Okay, so this is the mean position. So now let me draw some particles. So I'm drawing the particle at extreme and the particle at mean only. There are so many other particles between mean and extreme, but I am just drawing mean and extreme. Or maybe I can draw one more between mean and extreme. Every mean and extreme, I am drawing one more particle of the medium. So now as the wave is traveling this way, like the wave is going this way, this is the wave motion. Wave is moving towards your right. So now we have to tell that what are the particles that are moving up and what are the particles that are moving down. We have to tell this. So the particles at the crest, trough, they're always at rest. So crest and trough, they are at rest. They are not moving. Okay, fine. They don't move. But the particles between crest and trough, they move upwards. This is the rule, generic rule we have to remember. Any particle that is between crest and trough, it will be moving upward, while you have to consider the direction as well, that this wave is moving towards your right. This is the first thing that you have to look, and then you'll be saying, okay, this is crest and this is trough. So we have to make the direction of motion of these particles between crest and trough. Between crest and trough, 1, 2, 3 particles are there. So in which direction they'll be moving? They will be moving upward. So between crest and trough, they are moving upwards. So when I draw them, I'll say that at 2, as 2 is at the mean position, so its speed is maximum, so I will make a longer arrow. And at 1, it will be shorter arrow, and at 3, it will be shorter arrow as well. Why? Because the length of the arrow represents the speed. So the particle at 2 is having the maximum speed, and all are moving upward. Similarly, the particles between trough and crest, they will be moving downwards. So the particle between trough and crest, they will be moving downwards. And let me sketch them like this is the trough and this is the crest. So these are moving downward. Again, at mean, longer arrow, and then other one will be shorter. And at crest, there is no arrow. It means the particle is at rest. So now similarly, you can draw the particle oscillation for the other ones. So the main generic rule is that the particles between crest and trough, they will be moving upward. And the particles between trough and crest, they will be moving downwards. So this is how we can draw.
This is independent of the wave motion?
No, this is not independent of the wave motion. It depends on the wave motion. Like the wave motion is to right. If it is going to right, of course, you first have to look for the direction of wave motion. Then you will choose. You will be choosing if it is going from left to right. So first thing that you will choose will be the crest or trough that is to your extreme left. You will choose extreme left one. And then you say, okay, this is crest and this is trough. So between crest and trough, all are moving up. And then this trough and this crest, all are moving down. So that's the thing. If the wave is moving another way, of course, your particle oscillation will change. Right? So this is the generic rule. You just have to remember this rule along with wave direction motion, along with motion of wave, along with motion of wave. Okay, so after this, we can use this idea to do another important thing, and that important thing is predicting the new position of wave. Predicting or working out new wave position. This is just the drawing stuff. You'll have to draw the new wave position. So let's say if a wave is already formed over there. Okay, I have to skip one page. Okay, so let's say if this is the mean position and a wave is already drawn over there, and the wave is drawn like this, and the wave is going this way towards your right. This is the wave motion, and its time period or frequency, this is given to you. So let's say these are the particles, and let's say this wave is plotted at time instant t. So t is the time at which this wave is plotted, and they will tell you that, let's say its time period is 20 millisecond, or they will tell you that its frequency is 50 hertz. They can tell you any one of these things, right? So we say that time period or frequency will be given. Time period or frequency given. And they will ask you to draw the new position of the wave. So sketch new wave position after some given time. They will tell you the time. Let's say the first, they will say plot the wave after 5 milliseconds. Like t is this time at which it is already plotted, and now 5 more seconds are elapsed. Or second, they can ask you to draw the wave after 10 milliseconds. Or third, they can ask you to draw the wave after 15 milliseconds. And in the fourth, they can ask you draw the wave after 20 milliseconds. So these are the 4 questions that they can ask you to draw. So you just have to draw the new wave position. Okay, as all the particles are moving up and down, so of course their wave position is going to change. Let me tell you the method that you will follow in order to draw the new wave position. So first of all, what you'll be doing is you will be you know that if this is the particle, let's say particle 1, the particle oscillation, it will be like coming down from extreme to mean, this is 1, then to the other extreme, number 2, then coming back to mean, number 3, and then coming back to this, number 4. It means that in one oscillation of any wave or particle, in one oscillation, 4 movements are there. 4 movements. And what are those 4 movements? These 4 movements are between mean and extreme. Between mean and extreme. So 4 movements are there. Okay. So what we do is we will find the time for one movement. One movement means the quarter. One movement is quarter movement. Let's say if the particle is moving from mean to extreme or from extreme to mean, whatever, it's the same thing. So this movement will be one quarter of the movement. 1 quarter of oscillation actually. 1 quarter of oscillation. Okay, as this is 1 quarter of oscillation, so we will be finding the time for 1 quarter of the oscillation. So let's say if the time period is 20.
Okay.
Yeah.
Would it be half of the oscillation because there are 2 arrows? How is it 1 quarter?
Like in one oscillation, there are 4 type of movements between extreme and mean. 4, not 2. 4 movements. Like
yes, I know that, but between mean and extreme, won't it be half of the oscillation?
Yeah. Between one mean and one extreme. No. Mean and extreme, it will be quarter. Let me tell you. This is mean and this is extreme. So it goes from mean to extreme only. From mean to extreme one way. So this is quarter.
Not back.
Yeah, not back. This is quarter. If it goes back, then it is another quarter. So that will be half of the time period. But one way only is the quarter of the oscillation. Okay. So now what you do is you just divide time period with 4. You just divide time period with 4, whatever time period they give you. So 20 milliseconds is the time period, so divide it with 4, 5 milliseconds. So you will say that time for 1 quarter is 5 milliseconds. So 1 quarter of oscillation. 1 quarter of oscillation takes 5 milliseconds. And they've already asked you to draw the wave after 5 milliseconds. So you'll say, okay, after 5 milliseconds, that's fine. But the wave that is already drawn, you will draw the new position quite easily. Let's say this is the already drawn wave position. Like this. Okay, as there is only 1 quarter, as you've already seen that 5 milliseconds and 5 milliseconds is the 1 quarter of oscillation. So you'll be saying, okay, in 1 quarter, this particle will reach here. Okay, this particle, first you will make the crest and trough one only crest and trough. So this trough one will reach at the mean, the crest one will reach at the mean, like all the particles at the extreme will reach at the mean. What about between crest and trough? So this thing is important, as wave is going that way. So we have learned that the particles between crest and trough, they move in upward direction. So it will reach here. And the particle between trough and crest, they will be moving downwards. So it will be reaching at this point. And then this particle is between crest and trough, so it will be moving upward, so it will be reaching this point. And this point, it is between trough and next crest, so it will be going down, so it will be reaching at this point. So then what you do is you just draw a wave by joining all these points. So you will simply join these points together like this, and you will be making the new waveform. So this blue one is the new wave position. The red one was 5 millisecond, like before 5 millisecond and 5 millisecond later, the new position is the blue one. Now, if you want to draw for 10 millisecond, like what's the wave position after 10 millisecond? So we can say, okay, 10 millisecond means 2 quarters, because in 1 quarter it is 5. So 5 plus 5 is 10. So it means that 1 quarter, 1 quarter, 1 quarter, 1 quarter. So it will be half oscillation. So it'll be saying that it will be half of the oscillation. So let me quickly draw this for you again, and then over this concept will be completed. So let's say this was the wave drawn at time t. 10 millisecond elapsed means that now half of the oscillation. So every particle first you will draw all the crests, and then you will draw the particles between crest and trough. So this is 1 quarter and this is the other. So it means that they will be swiped. So all the particles will be swiped. The crest will become trough and the trough will become crest. And for the particles at mean, they will move up and down. So it means they will stay at their position wherever they will be staying at their position. Why? Because in quarter they move up and in another quarter they come down. So it means that all these particles, mean particles, will stay on their original position. So if you draw the wave, the wave will be like this. So this will be the new wave after. Okay, so that's how we draw the new wave position. So the main points that you have to remember in drawing the new wave position, So what are those main points that you have to consider? The first main point that you have to consider is you have to find time period. Sometimes what they do is they give you wave speed, they give you frequency, but they don't give you time period, right? So what you do is from the frequency you can find the time period. Time period is 1 over f. This is the first thing. Usually they provide time period, but if they don't provide, then you will be doing in this way. The second thing is you will be dividing time period with 4, and that will be 1 quarter of oscillation. 1 quarter of oscillation. And then with the given time, you will be aligning that. So let's say if your 1 quarter of oscillation time period is 5 milliseconds, and they ask you a time after 10 milliseconds. So what you do is with given time, whatever is the given time after which you have to draw the wave, you will divide that given time with quarter of time for the oscillation. So then you will get, let's say over here you get 2. It means that you will have to draw 2 arrows. One arrow means that from it is extreme to mean, and the other one from mean to extreme as well. So you'll have to draw 2 arrows, and that's it. And then the fourth and last thing is all the crests will go down, all the troughs will go up. Always the particle between crest and trough, they will go up. The particles between trough and crest, they will go down. It will be the fact that you will always be using. So we are done with the wave position, and now we have to move to another important thing, which is phase or phase difference. Okay, so the next important topic is phase. Phase is actually state. It's mean a state of particles, of medium, or state of wave. That let's say if in the water the wave is going, and we will say that what is the phase of the particles. So phase mean state of the particles. So phase is determined by 3 things. Phase of particles or waves is determined by 3 quantities. Okay, so what are those 3 quantities? The first quantity that we will be using is their displacement. Of course, displacement is always from mean position. The particles displacement from the mean position. The second one is their speed, and their speed is maximum at mean and minimum at extreme. The third one is their direction of motion. We know that the particles move along particular direction. Let's say the crest ones, they have to move down. The trough ones, they have to move up. The particle between crest and trough, they have to move up. The particles between trough and crest, they have to move down. So we have to look for their direction of motion as well. So let's say there are 2 types of phase. First is in phase, and second is out of phase. In phase and out of phase. Okay, what is meant by in phase? In phase means that if all the particles have same state. If the particles have same state, mean they have same displacement, they have same speed, and they have same direction of motion. So we say that those particles are in phase, and those particles are always lambda or multiple of lambda apart. Multiple of lambda apart. Like distance between them जो है वो क्या होगा, हमेशा lambda होगा, तो वो particles in phase होंगे. For example, we say all crests or all troughs, they are always in phase. सब crest आपस में in phase होते हैं, सब trough आपस में in phase होते हैं. क्यों? Because their displacement is same, which is maximum, their speed is same, which is 0, and their direction of motion is always the same. Out of phase means that they have different state. They have different state. Different state can be they have different displacement. The displacement is not same, or they have different speeds, or they have different direction of motion. Different directions of motion. So then we say that they are out of phase. So let me tell you one example through the wave through which we can identify in phase and out of phase particles. So let's say I have drawn 2 waves. Now there are some particles, like the first particle is here, second is here, this is particle number 3, this is particle number 4, this is number 5, this is number 6, this is number 7, 8, and this is number 9. So we have to tell that how many of them are in phase and how many of them are out of phase. So the in phase are the ones which are lambda part or multiple of lambda part. So I will say 2, 6, these are in phase. In a similar way, I can say 4 and 8, these are in phase. Similarly, I can say 1 and 5, they are in phase. Similarly, I can say 5 and 9, these are in phase. So the good thing about all these is that they are lambda apart. So the distance between them should be lambda. So they will be in phase with each other. And there can be many other combinations as well. I can say 1 and 9. 1 and 9, they are also in phase because the distance between them is 2 lambda. In the similar way, I can say 3 and 7. 3 and 7 are also in phase. Like there are multiple, there are so many combinations. So if the distance between two particles is lambda, 1 lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda, they are in phase. What are out of phase? Out of phase are the particles other than that. So you can say 1 and 3, they are out of phase. You can say 2 and 3, they are out of phase. You can say 1 and 2, they are out of phase. I mean, which are not lambda apart, they are out of phase. So 3 and 5, they are out of phase. 3 and 4, they are out of phase. So there can be many possibilities. So we say that the particles which are not lambda apart, other than lambda apart, or not multiple of lambda apart, so they are out of phase. Okay, now this is just the description of the phase. Now we have to discuss another thing that is known as phase difference. This is very important topic, not only for AS but for A2 as well, because these concepts go beyond AS. Okay, so we have to look for the phase difference now. Phase difference symbol is delta phi. Delta is the symbol for difference and phi is the symbol for phase. So that's why we say that phase difference is delta phi. Okay, so phase difference is a term and we have to define it as well. So phase difference definition is the fraction of wavelength between two vibrating particles of medium or between two waves in medium represented in terms of angle is known as phase difference. So this is the formal definition, the fraction of the wavelength between two vibrating particles of medium or between two waves. You can use any one of them in your definition if they ask. Why I've written or because it can serve for both, either for the particles or for the waves as well. Okay, so this is called phase difference. Now for the phase difference, the unit as it is in terms of the angle, so the SI unit is always radian. It is radian and it is represented by RAD. And the other common units that we can use, common units are the one that we use in everyday life. It can be degree. So radian or degree. And there is a relation between these two, that 2 pi radian is equal to 360 degree, or simply pi radian is equal to 180 degree, or pi by 2 radian is equal to 90 degree, or pi by 6 radian is equal to 30 degree. And in the similar way, if you say pi by 4 radian, so that is equal to 45 degree. So these are the conversions between angle in radian and angle in degree. So one thing that you can remember is that if the angle is having pi, then it means that it is given in radian. It is given in radian. Like if I say angle is pi by 3, it means it is understood it is in radian. It can never be in degree. Okay, so now we have to work out for the equations of the phase difference. So there are two equations for the phase difference. So
Okay.
yeah.
How will this be phrased in a question? This 2 pi radian thing. I don't get this.
How it will be coming in the question?
I don't know. सही है मुझे समझ नहीं आई पूरी ये radians वाली बात.
Beta, SI unit is radian. देखो, are you taking maths? No. So if
No,
you're not,
I'm very bad at maths.
you're not taking maths, so it means that you have to learn this. As we always measure the angle in degree, you never have measured the angle in radian even in your IGCSE level. But the SI unit for angle is radian. It is not degree. Degree is the common unit. Let's say if we talk about what is the common unit of speed that we use in everyday life, what will you say?
Meter per second.
Meter per second is the speedometer of your car in meter per second.
Kilometer per hour.
Yeah. Have you ever heard this thing? Someone is saying, I am driving at 100 meter per second, 20 meter per second.
I thought you were asking about the questions. I did not realize you were asking about real life.
Okay. So I said common. unit. Common unit is in everyday life, right? But SI unit is in your paper, but common means that it is in your everyday life. Okay. So the thing is, for the speed, the common unit is kilometer per hour. But the SI unit is meter per second. This is the SI unit, right? Same is for the angle. The SI unit for the angle is radian, RAD, radian. It is in your calculator as well, R. And then the common unit that we use is degree. So we say, okay, as we measure, you use protractor to measure the angle in degree, but we have to express in radian. So how you can express that? So I told you that for one complete circle, if you start your movement from here, for one complete circle, the angle that you have drawn is 2 pi radian. This is standard. 2 pi is standard. And then in common unit, it is 360 degrees. So we say, okay, both of these are equal. That's why I have written that for one complete rotation, the angle in radian is 2 pi and the angle in degree is 360. And then for half rotation, the angle is like if it is just half rotated. So for the half rotation, the angle is pi radian and this is 180. For quarter, if you just rotate it quarter like from here to here, that's it. This is called the quarter of oscillation. So if it is quarter of oscillation, then the angle is pi by 2 radian or it is 90 degree. Similar, it means that pi radian is 180. So whatever you have to find, you just divide that. If they say 30, so you will say that if you have to find that how many radians are there in 30, so you will use this. You will say 2 pi radian is 360 and you have to find how much is in 30. So you'll say x and then you cross multiply them and you will say x into 360 is equal to 2 pi into 30 and then x is equal to 2 pi into 30 over 360. So you solve them, this 0 goes away and this is 12 and this is 6. So you will say x is equal to pi by 6 radian. So you will say that in angle of 30 degree, the radian is pi by 6 radian. Okay, so one last thing that I need to tell for today is if here the angle is there in degree or radian and if I draw a wave over there, so you'll have to mention the angles over there. So let's say here angle is 0. So at this place it is 90 degree or it is pi by 2. At this place it is 180 degree or it is pi. At this place it is 270 degree or it is 3 pi by 2. And at this place it is 360 or it is 2 pi. So that's how we plot the angles along x-axis. So for one full wave, the angle is 360 or 2 pi. For half wave, it is 180 or pi. And for the quarter wave, it is 90 degree or pi by 2. Recording. Okay, so over today's topic is phase difference calculations, or you can say equations. So with a phase difference निकालने के लिए we will be using two type of formulas. Number one, phase difference is equal to 2 pi x over lambda. 2 pi x over lambda. And number two is phase difference is 2 pi small t over capital T. अच्छा, अब यहाँ पर why I have written two formulas. Let's say if I plot a graph for a wave and x-axis is distance or x-axis is time. So let's say if x-axis is distance and this is one wave, and you have to find phase difference between any two points. Let's say this is your first point P and this is your second point Q. So if you want to find the phase difference between P and Q, let's say they ask you find phase difference between P and Q, and you will see that x-axis is distance. X-axis is distance. Then you will be using this formula: delta phi is equal to 2 pi x over lambda. What is lambda? Lambda you already know. Lambda is the wavelength. Lambda is the wavelength, which is the wavelength of one wave. Like this is the distance, which is lambda. Crest ultra. Yeah.
The point being, I don't know this. Can you explain this whole thing again?
P and Q. Look, this is a wave. This red line is a wave. This is a simple wave, a transfer wave. P and Q are just 2 points on the wave, right? They can be anywhere on this red wave. Their position can be anywhere. Let's say I've drawn them on the crests of the two. And they can ask you, okay, this is point P, this is point Q. You have to find phase difference between these 2 points. That what is the phase difference between them? And earlier we have seen what does it mean by phase difference? The fraction of wavelength between two vibrating particles of medium or between two waves in the medium represented in terms of the angle is known as phase difference. And one more thing previously we have looked upon, that what is meant by phase. Phase means state of particle of medium. Phase of particle is determined by three quantities. One, you will have to look at their displacement from their mean position. Second, what is their speed? Third, what is their direction of motion? If all three things for two particles are same, then those particles are called in phase particles. But if any one of these three or two or three are different, we say these particles are out of phase. Phase means state. Let's say we say that in Bahria town or DHA phase 1, phase 2, phase 3. So if two or three students are there and they're saying that we are living in phase 1 DHA, it means that they are living in same sector. They are living in same area, right? They belong to same area. And if one is saying that I'm living in phase 1, other is saying I'm living in phase 2, it means they are living in different areas, so they are out of phase. So that is what we meant with phase in the wave. So phase is just the state of the particles. State. Okay, so let's get back to this. I'll explain this more for you. Let's say this red one is the wave and P is the particle at this point, Q is the particle at this point, and they're asking us, you have to find the phase difference between these two particles, that whether they are in phase, out of phase, what is their phase difference. So we'll say, okay, the first thing that we need to look upon is the x-axis quantity. What is x-axis? Either it is time or it is the distance. Hold on a minute. Okay, the mosque is next to our house, so okay. Okay. So the thing is that the first thing that you have to look is the axis value, axis, that whether axis is distance or axis is time. So once you sorted out that it is distance, so you will shift to this formula. You say, I'll be using delta phi is 2 pi x over lambda in order to find the phase difference between the two particles. Okay, this 2 pi is fixed. It will never change. Lambda will be the wavelength of this wave, whatever it is. X will be the main thing that we will be looking upon. X will be the distance between these 2 points between which you have to find the phase difference, right? So X is the distance between those two particles for which you have to find phase difference. Lambda is the wavelength and 2 pi is the fixed thing. So if I solve it for you, I'll be saying phase difference is 2 pi. And what is x? So as you see that the both particles P and Q are at two crests. So what is this x equal to? Can you tell me what is this x equal to?
Half of the wavelength.
Half of the wavelength. How half of the wavelength?
Or
What is the distance between one crest and next crest? It is one wavelength.
no,
It is one wavelength. You know what? Yeah, it's one
okay.
wavelength. Let me take you back to where we
No, I
have.
think I did wrong.
Yeah, like here. You can see here what about the wavelength. The wavelength is the distance between the two crests. So it means that the distance between these 2 points P and Q is equal to lambda. So you'll be saying, okay, it is equal to lambda. And what is this lambda equal to? If x-axis don't have any value, then you say that lambda is lambda. Like, I mean, if there is no labeling over there. So what you do is you cancel them out. So you'll say it is 2 pi radian or it is 360 degrees. So you will say that the phase difference between P and Q is 360 or 2 pi radian. So we say phase difference between P and Q is 2 pi radian or 360 degree. Now, if I draw another wave and I'll ask you to find the phase difference, let's say this is the wave, and let me mark the values as well for you. Like all these values are already marked over there. This is, let's say, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. So this is 0.7. And now the points, the 2 points, one point is this, which is x, and the other point is this is y point, this point. So now you have to find the phase difference. Now you have to find the phase difference between x and y.
Sir, will we open the 2 pi or will just leave it as it is?
You will be using this formula now.
Yes, I know, but okay.
Yeah, you'll be using this formula. And the same thing that we have done before in the first part. You'll be doing the same thing. So let's try to solve it.
Give me 3 minutes.
Okay.
sorry, 4.71.
4.71 4.71 आपने कैसे निकाल लिया बेटा?
Where the wavelength is 0.4.
2 pi, actually you use this, why? Because x-axis is time. So 2 pi, t means that it is the distance between x and y. It is the distance between x and y, time between x and y. So the y is 0, x is 0.2, 0.3, 0.4, 0.5. So y is 0.5. So 0.5 minus 0.2 is 0.3. Yeah. And then the time period is how much? 0.1, 2, 3, 4. It is 0.4. Right? Yeah. So this cancelled away. And this is 6 pi by 4. So this is 3 pi by 2 radian. Yeah. And you have
Sir, I open it right now.
नहीं, you have to solve it. 1.5 pi, अब इसको जब आप solve करोगी तो what you get?
17.
4.17 radian.
4.71.
71. Okay, that's fine. Yeah, that is fine. 4.71 radian. Yeah, this is fine. So this is the phase difference concept. Now let's apply this on two waves. Two waves, phase difference. We did was on two particles on the same wave, but now we are doing it with two different waves. And the two different waves must be traveling in the same medium. So let's say this is distance and this is displacement. And let's say I am going to draw the first wave as this. This is the first wave. And then for the second wave, let's say second wave is having a little bit more amplitude. So let's say second wave is this. This. So this is, let's say, wave P, and the other one is, let's say, wave Q, and both the waves are coherent. Coherent wave means that they have same frequency, same time period, same wavelength, same speed, but their amplitude can be different. Amplitude can be different. So if there are two waves for which they have same frequency, time period, speed, and wavelength, we say that those waves are coherent waves. Okay, so now you have to find phase difference between P and Q. Find phase difference between P and Q. Okay, so in order to find this, again, we'll be looking, the first thing that we will look upon is x-axis. What's the value? So the first thing is whether you have to look upon x-axis, that whether x-axis is distance or time. So we say it is distance. So we'll be using the formula for having distance. So the formula that we use will be phase difference equal 2 pi x over lambda. Okay, once we are done with this, we'll be looking, next thing we'll be looking upon is what is the value of wavelength, and next thing will be what is x between them. So first we look upon this lambda. So as x-axis is not marked, if it is not marked, and both these waves are coherent waves, so for wavelength we'll be using lambda because x-axis is not labeled, nothing is written, that numbers are not written. So if numbers are not written, then wavelength is wavelength, that's fine. What about x? If wavelength is not given in numbers, it will be in terms of lambda then. So x will be in terms of lambda. So what is x? So x is important here. You have to look for the identical parts. So this is the crest and this is the crest of blue crest and red crest. So you have to look for the identical parts which are closest to each other. So the distance between them will be x. So and similarly, you can do with trough as well. I mean, this is the trough and this is the trough. So you can look for this distance as well. Otherwise, from here, blue wave is coming down, red is coming down. So at this point, this distance will be x as well. In the similar way, blue wave is going up, red is going up at this point. So the distance between them is x as well. So x is, you can take any of these x as the value of x in the formula. So x means that what is the distance between the closest identical points of the two waves. So let me write it over here. So we say distance between closest identical points. So the distance between closest identical points is x. So if we look here, that this distance seems to be lambda by 4. How it is lambda by 4? Let me tell you that if we just look upon this, so this is 1/4 of the wave, the one that I am shading. So the distance from this top of the first to the top of second is actually equal to lambda by 4, because this distance is equal to lambda by 4 because this is 1/2 of the crest. So half of the crest is lambda by 4. So we'll be saying, okay, this x is actually equal to lambda by 4, and lambda is lambda. So just plug in these values into this formula. Delta phi is 2 pi x over lambda, and 2 pi x is lambda by 4 over lambda. Lambda goes away, and then in the similar way, lambda goes away, and this 2 2s are 4, so you're left with pi by 2 radian. So you say that the phase difference between these 2 points is equal to pi by 2 radian, or it is equal to 90 degree, because pi is 180, so 180 over 2 is 90 degree. So you can tell this as well, or you can write in the radian as well. I mean, if you want to write in the radian, so you will be dividing pi with 2, so that will be 1.62, and that will be in radian. Not 62, sorry, not 62. It will be, oh no, yeah, 62. Okay, so that's how you find the phase difference between the two waves. It's very easy. You just have to use the same formula, but what you have to do is you have to look for the distance between the closest identical points. It can be the two closest crests of the two waves, or it can be two closest troughs of the two waves, or it can be the 2 points on the mean position from which both the waves are going down or both the waves are going up. So the distance between both these points will be x or t, depending on what is on x-axis. Is this thing clear, Beta?
Yes.
Okay, right. So okay, so we are done with phase. So let's move on to the next thing. Hold on, we are done with phase, and we are done with particle motion, wavefront, and we are done with wave speed, wavelength, and speed as well. Okay. Okay, so let's move on to the next thing, which is okay, which is intensity. But before we go to intensity, let me tell you about monochromatic wave or light. What is meant by monochromatic? Mono means one. So if a wave is having only one wavelength, it is called monochromatic. Why I'm saying this? Because there are so many other waves which are having multiple wavelengths. Let's say white light. White light is having 7 colors, so each color is having different wavelength. In the similar way, many other waves have 2 or 3 wavelengths, but monochromatic wave or light is the one which is having single frequency or single wavelength. So we say a wave having single frequency or wavelength is known as monochromatic wave. Okay, for example, if we say red light, so red light is monochromatic. Why it is monochromatic? Because it is having only one wavelength, which is equal to 700 nanometer. So that's why we say red color is monochromatic. So the single color lights all are monochromatics. Point to remember, all single color lights are monochromatic, and white light is not monochromatic. White light is not monochromatic. Why? Because it's having 7 colors and 7 wavelengths are there. Okay, but after this we have to look upon this was a very short concept. Now we are going to move on a very important topic after phase difference, that is intensity of wave, or sometimes referred as wave intensity. Okay, so what is wave intensity? Intensity का meaning क्या होता है? Intensity is basically strength. Let's say if you're sitting in the room and you have switched on only one light, so the light amount will be less. When you switch on 2 lights, 3 lights, 4 lights, 5 lights, and you keep on increasing the lights, then what is increasing? The light intensity is increasing. Why? Because you are increasing the number of sources that are producing the light. So intensity of wave is actually amount of the wave, but its definition is slightly different. The definition is energy transferred by a wave per unit area per unit time is known as wave intensity. So we say energy transferred by a wave per unit area per unit time. So intensity is energy transferred. So energy transferred per unit area per unit time. So that's how we can write the formula for the intensity. And if we talk about its unit, the unit of energy is joule, the unit of area is meter square, and the unit of time is second. So that's how we can write its unit. It is joule per meter square per second. There is another definition for this as well. If you just simply look upon energy over time, so energy over time, or if you look upon joule over second, so that is equal to power. So we can define intensity in terms of power as well. So we say power transferred by a wave per unit area is known as wave intensity. So one is in terms of energy, and the other one is in terms of power. So for the equation, we can write I is equal to power over area. And if we want to write its unit will be watt per meter square, because unit of power is watt and unit of area is meter square. So that's how we define this intensity, and it is a scalar quantity. So the two units, one is joule per meter square per second, our second unit is watt per meter square. Now we have to look upon factors of wave intensity. Like if we want to increase the intensity of the waves, how we can do that. So the first thing that we can do, the first factor for intensity is intensity proportional to amplitude square. So it means that it is I proportional to A square. I mean, if you increase the amplitude 2 times, the intensity increases 4 times. If you decrease the amplitude 3 times, the intensity decreases 9 times, because that is the square over there. So we can write it as I is equal to constant A square, where K is the constant. A is the amplitude of wave and I is the intensity. So you can use this formula to find the wave intensity. Let's just explore its example. Let's say here is the distance and here is the displacement. And let's say I'm going to draw one wave. That is, wave is like this. Okay, so let's say this is its amplitude, which is 1 division. Okay, so we say that its intensity is I. So there's a second wave and its intensity is 4I. So its intensity is 4I, but its frequency, wavelength, speed is same. So draw that wave on the graph. So this is the data for the second wave. So you're supposed to draw the waveform on it. So what we'll be looking at is, okay, just zoom in. So we'll be looking at, okay, its intensity is 4I. So we say, okay, how should we draw the amplitude? So we'll be using the factor I proportional to A square. So for the first wave, the intensity is I, and the amplitude is how much? It is just 1 division, like 0 to 1. So this is 1 division, so 1 square. 1 with 1, I mean this, 2, 3, 4. Okay, now the new intensity is 4I, so we write 4I. What is the amplitude? So x square, you have to take the square, because in the formula it is I proportional to A square. So you cross multiply them. When you cross multiply them, you'll be saying it is x square into I is equal to 4I into 1. So I goes away. And then when you solve it, x square is equal to 4, and you take its square root, so x equal 2. It means that the amplitude of new wave should be 2. So you should be drawing the new wave till this point of 2, and you'll be keeping the wavelength and frequency the same. So let's say I'll be drawing it like this. So this is your new wave, which is having 4 times the intensity. In the similar way, if I ask you to draw a wave, let's say the first wave is having amplitude of this. Here is the time, and here is the displacement in centimeters, 0. This is like 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so now you have to draw a second wave. The intensity of the first wave is I naught. The intensity of the second wave is I by 2. It's half of this. So draw a new wave. Okay, so you should be drawing this yourself. So after doing this, x is 3.5. So you'll be drawing it like here, because you have to keep the frequency and time period the same. So that's how you can plot it. Okay, so we are done with the first factor. The first factor for the wave intensity is intensity proportional to amplitude square. So like if you increase the amplitude 2 times, intensity increases 4 times. If you decrease the amplitude 3 times, intensity decreases 9 times. So this is the formula, I is equal to KA square, where K is the constant over there. So that was the first factor. We have to look upon the second factor now. So the second factor for intensity is frequency. So intensity directly proportional to, or hold on, first I have to write the factor name, which is frequency. Frequency of wave or source. So that is the second factor that can affect the wave intensity. So it is how it affects intensity directly proportional to frequency square. So intensity proportional to frequency square, intensity is equal to kf square, the same way as the amplitude. So for instance, we have one wave, its frequency is f and its intensity is I. So for the second wave, let's say you double the frequency, so its intensity will be 4 times, because if you increase the frequency twice, the intensity will be increased 4 times. Okay, so same is this thing. So let's do an example. There is a wave having a frequency of 250 hertz and its intensity value is 10 joule per meter square per second. So if we make its frequency as 1000 hertz, what should be its new intensity? Okay, let's try to find it and try to find it yourself. The first intensity was 10, the new is 250, so 250 square. New intensity you have to find, and the frequency is 1000 square. And you simply cross multiply them. So it is x into 250 square equal 10 into 1000 square. So you simply solve them and you will get your answer. 1000 over 250 whole square. So 16, 254 and 4 square is 16, 16 tens are 160. It is coming out to be 160 joule per meter square per second. Why? Because you have to use this expression, intensity proportional to frequency square. So what you do is you first write the first intensity, which is 10, which is 10. So you write 10 over there, and then you have to write its frequency, which is 250. So it is 250, and you always have to take the square because frequency square is there. And then for the new intensity that you have to find, you'll be writing x over there, and its frequency is 1000. So you write 1000, you take square because frequency square is there. Then you cross multiply them, and you get this. Shift 250 square on the other side, it will be 1000 square over 250 square. So this will be cancelled away. So 16 tens are 160. So that's how we say that the new intensity is 160. This is one way. The other way is factor method. You can see that how many times frequency has changed? 4 times. So you say that frequencies increase 4 times. So if intensity proportional to frequency square and frequency increase 4 times, so 4 square is 16. It means that intensity is going to increase 16 times. 16 times of what? Original. What was original? 10. So that's how it is 160 hertz. So you can do this way as well. Is it clear? Okay. The next factor for the intensity that we have to look is the distance from source. Distance from the source. What does this mean? We have to look at how much is the distance of the point at which we have to find the intensity is from the source. So for that factor, it is I proportional to 1 over d square, where d is the distance of point from source. And this is also known as inverse square law. Inverse square law. And this is universal law because it is applicable to everything, to every wave and every radiation. This law is applicable. So that's why we say this is inverse square law. So I inversely proportional to d square. So for example, and one more thing, if we want to convert this, we'll be saying I is equal to k over d square, k is a constant. So id square is equal to k, which is constant. It means that whatever the distance is, you simply just multiply that distance with the intensity at that point, you'll always get the same answer. So for example, this is the source, it is producing the waves. This is point P and this is point Q. So let's say, okay, let's say the wave is coming from S, which is source, to P and then to Q. So we say that when it reaches at P, its distance was X and its intensity was I naught. And the distance from P to Q is 3x. What should be the intensity at wave at point Q? You have to tell that. So what we do is we'll be using I proportional to inversely proportional to d square. This is the, or you can say I proportional to d minus 2. You can do this way as well. Okay, so now we'll be saying that first look at point P. So at point P, the intensity is I naught and the distance from the source is X. So X square. Okay, then for point Q, intensity you have to find, and the distance from the source is 3x plus x. So the distance will be 3x plus x, it will be 4x. So you'll be saying 4x, and then don't forget to take the square because the square is there. Now, what you'll be doing is, as it is inverse proportion, so whenever it is inverse proportion between the two quantities, and you are using the ratio method, and it is inverse proportion, so what you'll be doing is you'll be linearly multiplying them. You'll be multiplying them linearly like this. Don't cross multiply. We cross multiply if they are directly proportional. So solving it, you'll be getting I naught into x square equal IQ into 16x square, because you expanded 16x square. X square gone. So you got I naught is IQ 16, but you have to find IQ. So you shift 16 to other side, so it will be I naught by 16. So it means that the intensity will be 16 times less than the intensity at P. So intensity will be 16 I naught divided by 16. Or you can just divide it as well, like 1 divided by 16, and you will get the answer, I guess, 0.09, no, 6. Yeah, 0.06 I naught. That will be your intensity. Is this clear, beta?
No?
Yeah.
Yeah, I got it.
Okay, you got it. Okay, so this was the third formula. So summing up about intensity as this is important wave phenomena. So let me tell you the thing that how we define it. So its defining equations are two. If you want to define the intensity, there are two ways. One is it is energy transferred by a wave per unit area per unit time, or the second way is intensity is power transferred per unit area. About the units of intensity, it depends on the formula, of course. So the first is joule per meter square per second, or the second is watt per meter square. The third thing about intensity is its factors. So we studied three factors for intensity. The first factor was intensity proportional to amplitude square, second was intensity proportional to frequency square, and the third factor was intensity inversely proportional to distance square, which is called inverse square law. Okay, so now let's do one question related to this in which we'll be using intensity and phase difference together. Okay, let's solve one question related to phase difference and wave intensity. This question is from old spec paper 2018, question paper 21, and question number 4. For the progressive wave state, what is meant by state? When they say state, you just have to simply write them, the period. These are the definitions you can do that. Time required for one oscillation, and the wavelength is the distance between two in-phase points. That's easy. The real question is this. Figure shows the variation with time, x-axis is time, of the displacement of two progressive waves P and Q passing through the same point. So this is wave P and this is wave Q. P is having greater amplitude and Q is having lesser amplitude. So amplitude of P is greater than amplitude of Q, but both the waves have same time period and same frequency. How do we know this? We know this because they have said the speed of the wave is 20 centimeter per second. So both of these waves have same speed. Why? Because the speed of the waves depends on medium. Depends upon medium. If both the waves are traveling through same medium, they have same speed. Frequency depends on source. Depends upon source producing the wave. And the wavelength depends upon medium again. Why? Because V proportional to lambda. So both speed and wavelength changes in the same way. So if we look upon this, so we say that the time period of this wave is 0.60 second. I have looked for wave P. Can you look for wave Q? If you look for wave Q, you'll be saying, okay, this is my first point, and the wave is going over there. This is crest, and this is trough. So this is 0.8. So you subtract these two together. So the wave time period is 0.06 for Q as well. So that's why I said that both these waves have same frequency, same time period, same wavelength, and same speed. Okay, so the time period is 0.6 second, and the speed is given as 20 centimeter per second. They're saying calculate the wavelength of the wave. So we say V is equal to F lambda, and lambda is equal to V by F. So you just put the value. V is 20 centimeter per second. And what is the frequency? So we say that frequency is 1 over T. So T is 0.60. So you just solve it, and you put it over here. So this goes up, and it will be 12. And second cancel the way, and you're left with centimeter. So it means that its wavelength is 12 centimeter. Moving forward, determine the phase difference between the two waves, delta phi. So you have to find the phase difference. So as I told you before, that if you want to find the phase difference, you first looked upon what is the axis. The axis is time. It means you'll be using the value, the equation of the time. And then the formula for this for phase difference is 2 pi small t over capital T. So capital T is this 0.6, which is the time period. And now you have to look for the small t. Small t is the distance, is the difference between two identical parts. This is important to note. Let's say the first wave P is going from here upward. The second wave is going from here upwards. So you can say that this is the distance between the identical point, that is 0.20. So you can say that the small t is 0.20. You solve it. And when you solve it, it will be 2 pi by 3 radian. 2 pi by 3 radian. Or if they are asking in the degrees, yeah, they're asking in the degree here. So you'll be saying 2 pi over 3. And don't convert this pi into 3.142. Why? Because they're asking in degree. So convert this pi into 180 because you know 1 pi is equal to 180 degree. So convert into that, and then 3 6 are and 0 and 6 2s are 120. So it means that the phase difference between them is 120 degrees. Next is calculate the ratio of intensity of Q to intensity of P. Like you have to find intensity ratio of intensity of both. तो बेटा अब यहाँ पे हमें ऊपर क्या पता है, frequency पता है ना, या amplitude, sorry, we know the amplitude as well. दोनों का amplitude हमें पता है. तो let's just go to the amplitude and see कि इनका amplitude क्या है. तो wave P का amplitude आप देखो कितना है, that is 3 millimeter. और wave Q का amplitude देखो क्या है, that is 2. तो इसका मतलब ये है कि 3 और 2. तो as we know that intensity is KA square होता है, तो यहाँ पे हम लिखेंगे KAQ square over KAP square. And then what's going to happen कि ये जो K और K कैंसिल हो जाएगा, और AQ जो है, Q का जो एम्पलीट्यूड है वो 2 था, और P का जो एम्पलीट्यूड है वो 3 था. तो आप इनका स्क्वायर ले लोगे, 2 का स्क्वायर 4, 3 का स्क्वायर 9, और 4 ओवर 9 करोगे तो आपके पास आएगा 0.44. So the ratio will be 0.44. So that's how you can find the wave intensity. Is this thing clear?
Yes.
Okay, so let's go to the last part. The two waves. Okay, no, this part we still have not done, so we can simply skip this part for the moment. Okay, so that's enough for today. For the next lesson, we'll be looking upon Doppler effect.
Sir, can you send the notes and the recording of yesterday's class as well and today's?
Okay, I'll send you the notes first, and I'll have to combine all the recordings together. So I'll try that. I'll combine these today, and I'll send you. So Doppler effect
Okay.
plus one more thing is left. Yeah, I forgot that. CRO. CR is also left. So it means that
Sir, can you also compile the electricity chapter
for the notes.
for the recording, because
Yeah, I
on
have.
the last day it captured my hand, so I didn't.
Okay. I'll have to do that as well. I'll do. Okay.
Okay.
Okay. Allah Hafiz. Okay, Beta, so as you know that we are doing waves, and in the waves we are left with few topics. The first topic that we'll be touching today will be this, number 3, which is the cathode ray oscilloscope, CRO. This is a device that we'll be using to measure the frequency of any frequency of waves and amplitude of any waves. Whether it is like sound wave, electromagnetic wave, we can use CRO to measure their frequency and amplitude. Next, we are done with all these things. We'll be looking upon some how we are already done with this, compare transverse and longitudinal waves, analyze and interpret graphical representation. We are already done with that, but we will be touching that part, the graphical part as well. The next topic will be the Doppler effect for the sound waves. This is very important topic. And then after this, we'll be looking quickly upon electromagnetic spectrum, and then the main topic will be polarization. So polarization is the important topic, and that's it. So then we'll be moving on to the next topic in the next class, which is superposition. So right now, our first task today is, yeah. So today is 2nd of April. Okay, so yeah. Okay, so the first topic that we are looking at today is oscilloscope. So it is CRO, or we say it is cathode ray oscilloscope. Okay, so what are the meanings of these? Cathode ray oscilloscope, cathode actually is the name of the electron. So these are the electrons. The first name given to electrons after their discovery in 1897 by J.J. Thomson, it was cathode ray. Later, it was given the name of electrons, and others were protons and then neutrons. That's why this was given the name of electrons. So cathode rays are what? These are simply electrons. What is oscilloscope? Oscilloscope is a device that plot graphical description, like that will show that will convert anything into a wave. Let's say if I'm talking my sound waves, and then the oscilloscope will be converting my sound wave into a waveform that I can see. So oscilloscope is just a wave plotting device. So we can also say it is wave plotting device. So for the cathode ray oscilloscope, we can say it is a wave plotting device. Next thing, it can be used as in waves. It can be used as a timer. As a timer means to measure very small intervals of time. To measure very small time intervals. Like that, we humans cannot measure, like 0.002 seconds, we cannot measure with precision. So this oscilloscope will be measuring the small times with high accuracy. And one more thing it can do is, it can be used as, you can say, a voltmeter. Voltmeter, why? So that we can measure peak voltage, sometimes known as amplitude, peak voltage or amplitude of waves. So we'll be looking upon two uses of this CRO, one as one as a timer, and the other one as a voltmeter. So that is what in our syllabus. And of course, it is wave plotting device as well. It can convert your sound wave into a wave. It can convert alternating current into a wave. And we use this in everyday life in ICU, the machine which is connected to the body of the patient, and that displays the heartbeat or heart rhythms. That is also called CRO. And in old times, we used to watch the television that are the glass screen and the big boxes. So those televisions with the glass screen and big boxes, those are also called oscilloscope, because in that, for image projection, electrons were being used. Nowadays, we use LED, LCD. So these are not the oscilloscopes, but those were the glass screen ones. Those were also called cathode ray oscilloscopes. Okay, so after this, we'll be looking upon just its we can say its image, how it looks, how it look like the CRO. So it looks like a tower casing of a CPU attached with a computer. So let's say this is the CRO, and then there is a grid on it. This is called the grid or the screen. It is having the graph. As it is having the graph screen, that's why it's called grid. The waves are displayed onto it, and then there will be some switches on it. This will be the first switch. This will be the second switch. The first switch is called gain, and the second switch is called time base. I'll explain these as well, that what are their roles. And then we'll have some connectivity, like this is the positive terminal and this is the negative terminal. So these are called Y terminals. Like we attach the mic with these, or we attach the alternating current through wires with these two terminals, and then a waveform is going to display over here on the screen. Whatever waveform is, it will be displayed on the screen. If you want to make the sound wave, then of course the mic will be connected to this. Let's say this is the mic, and it is connected through these wires to the CRO, and when you'll be talking into it, when the sound will be coming, the mic will be converting it into electrical signal, feeding it, and then the electrons will be making the waveform of that sound over there. So that's how it works. Okay, after this, we'll have to look for its controls or switches. As you know, on a television remote control, there are many switches, but few of them are that can be used to control the zoom. So you can zoom in the picture, you can zoom out the picture, you can make picture bigger or smaller. In the similar way, we can control the waveform that is formed on the screen with the help of these two switches, one of which is gain, another one is time base. So let me tell you about the first one, that is gain. There's another name for gain as well, that is called Y sensitivity. Y sensitivity. Okay, so Y sensitivity means that, let's say, let me tell you about that. That let's say if there is this is the screen of the CRO, because usually only the screen is made, not everything that I have drawn. They usually only make the screen. So let's say if a waveform is drawn over there, and the waveform is like this, right? Or I can make a second one as well, a second scenario in which another waveform is there. This is the second, let's say, situation.
I'm sorry, I cannot hear you. Sir, I cannot hear you.
Okay. Now you can hear me, right?
Yes, now I can.
Okay, so I was telling you that what is common in both of these things. In both of these things, it's harder to read the amplitude. Why? Because here it is too small, and here it is too large. So what we do is we will use this gain. We will use this gain switch, and we will change the setting of this gain or Y sensitivity so that we can make the wave in such a way that we can read its amplitude easily. So the thing is, over here we have to increase the amplitude, and over here we need to decrease the amplitude. So how we gonna do that? We will be using the gain switch. So the gain or the Y sensitivity will control the height of wave. So let's say what we have to do is we have to zoom in here and we have to zoom out here. So we have to zoom in and we have to zoom out here. And that can be done only by changing the gain setting. So let me first write the equation for this. The equation for this is peak voltage, or sometimes it is also called amplitude. Peak voltage or amplitude is equal to gain. Sometimes it is written as Y sensitivity, both are the same things. So gain or Y sensitivity into number of squares or centimeter in peak height. Peak height mean maximum height. So this is your formula, which you have to remember, which you will be using in the question. So if I can just short it down, so I can write V naught is equal to gain G into, for this, I can write X naught. This is sort of amplitude thing, that how many maximum squares are there in the height of the wave. Why squares? Because actually this whole thing is in the form of a graph. As I already told you that there are the graph lines, the graph grade is there. So you can easily see that how many squares are there in the height of the wave. So it will be like this. Later I'll be showing you the question as well for this. But anyways, this is your amplitude or peak voltage of the wave. This is your gain, which will be given to you in the question, and this will be X naught that you will be measuring yourself. You know yourself. You'll be looking into that how many squares are there in the peak of the wave. So gain is in millivolt per division or millivolt per centimeter, and it is given in question. Let me further elaborate it. That what is meant by this. So the unit of gain will be millivolt per division or millivolt per centimeter. What is division or centimeter? Because this question must be coming into your mind that what is this thing division. So let me redraw quickly again. This is the CRO screen, and as I told you, there is a graph grid. So let's say that grid will be like this: 1, 2, 3, 4, 5. 5 squares up, and 1, 2, 3, 4, 5. 5 squares down, and this is your central line. So in order to differentiate it, I'm just drawing it with the red so that we can easily figure out where is the central line. And then of course here 1, 2, 3, 4, 5, and 1, 2, 3, and 4, 5. So this is over grid, and now you can see that how many squares are there on it. There are like too many squares. So the one square is called one division. The one square is called one division. So let's say we say that this one box y-axis is called one division, or sometimes it is called 1 centimeter. In the similar way, x-axis is called one division, or it is called 1 centimeter. Either of them can be there. So if they say that the value of gain is 20 millivolt per division, what does this mean? One division along y-axis represents 20 millivolt. This is what is meant by this gain value of millivolt per division. So if I say that there's a wave plotted over there, and that wave is like this, the wave is like this. So we can say that how many, this is the mean line. So how many boxes are there? 1, 2, 3, 4. So we say in the peak there are 4 boxes. So if the gain is 20, what should be the peak value over here? Peak value is gain into X naught. So you say, okay, they have given us the gain as 20 millivolt per division. And what is X naught? X naught is number of boxes: 1, 2, 3, 4. So 4 boxes are there, 4 divisions are there. So this division cancels away, and you got V naught as 20 millivolt. So you will say that the
Sir,
peak of this is 20 millivolt. Yeah.
so gain would be always 20, or would it change?
No, gain's value is changed. It's just 20 is just the value that I'm telling you. It can have any value, but its unit will always be this: millivolt per division, millivolt per centimeter, or it can be volt per division, or it can be volt per centimeter. These are the units. Units will be fixed. The value can change. Yeah, value can be changed. Okay, so let's move on to the next thing. This was the first thing related to gain. Gain is the Y sensitivity. It controls the movement of the wave along Y-axis. If you want to make the wave bigger or smaller, you will be using the gain. And one more thing, gain is equal to peak voltage over X naught. So the thing is, if you want to, X naught is the amplitude. If you want to increase X naught, that wave is very small, wave, very short wave. If very short wave is there and you want to increase it, so obviously you want to increase X naught because X naught is the amplitude. So if you want to increase X naught, this V naught is constant actually. If you want to increase it, you have to decrease gain. So it means that you're going to decrease the gain's value in order to increase the amplitude of the wave. Similarly, if the wave is too long, too high, so that it's not be plotted on the screen like this in the second, you cannot see the peak. The peak is not there. It means amplitude is too high, and you want to decrease it. So the next thing is, if you want to decrease the amplitude so that you can plot it easily, then how you can do that? What you have to, so you'll be saying that as gain is V naught over X naught, and you want to decrease X naught, it means that you will be increasing the gain's value. So you say that the gain must be increased. Gain is just a reading. It is just a switch. You will just switch. You'll just move it to the higher value, and then you can increase the gain. Like if I quickly tell you about the gain, so that let's say the switch, it is the switch which is, let's say, which is pointing over here, let's say first. So this is the switch. So there is a 0 reading, here is 10 reading, here is 20, here is 30, 40, 50, 60, 70, 80, 90, and 100. And it is in millivolt per division, let's say. So if you want to increase it, you will simply move this dial to the higher value. That's how you can simply change the gain's value. The second thing is time base or X sensitivity. Okay, time base or X sensitivity. Okay, so what is meant by time base or X sensitivity and how we use it? The thing is, it's as the gain was controlling the y-axis movement. In the similar way, this will be controlling the x-axis movement. Like the time will be controlling the x-axis movement. So how it will be controlling the x-axis movement? Let me tell you about that. Just yeah. Okay, so let's say again, I'm quickly making the two graph grid just to show you that how this will be helpful for us. So let's say there's a first wave, and the first wave is like this. So you can see that too many waves are over there. And for the second one, you can see that not a complete wave is over there. So we say here too many waves, and here incomplete wave is there. So what you want to do is you want to stretch the wave here. What is our objective? In the first diagram, stretching the waves. Stretching the waves. Why? Because we can read them easily. And over here, what we have to do is compressing the wave. We have to compress the wave because of it. It's very long. So we have to compress the wave so that we can read it easily. So our objective is that we have to read them easily. Why? Because look, there's a formula. Time period equal time base multiplied by wavelength. So this is the formula, as we have one formula for the gain, which was peak voltage is equal to gain multiplied by height of the wave, x naught, which is some kind of amplitude. And in the similar way, time period is equal to time base into wavelength. What is wavelength? This is number of division or centimeter in one wave. That how many divisions are there in one wave. And of course, the divisions are always there, like 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And similar way, x-axis 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So you have to read that. So you can see that it's very hard for you. If I say in how many boxes one wave is there, so it will say that it is very hard because the wave is compressed. And in the similar way, if I ask you 1, 2, 3, 4, 5, if I ask you for this one, so 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. If I ask you for the second one, that how many squares along x-axis one wave is, so you'll say, sir, one wave is not there. So what I'll do, okay, I'll say that in the second diagram, just compress it so that you'll be able to see one wave. And in the first diagram, I'll say, okay, stretch the wave so that you can easily see that how many divisions are there in one wave. So for that, you will be using this formula, which is time period equals time base into wave length. Okay, so what is this? What is the unit of time base? As I told you that the unit for the gain was millivolt or volt per centimeter or volt per division. In the similar way, this time base is having the unit of millisecond per division or second per centimeter, whatever. And you can see 1 centimeter or 1 division is this one block along x-axis. So what is the role of time base? We say that time base can be used to stretch or compress the wave along x-axis. As gain was used to increase the height or decrease the height of wave along y-axis, so time base is doing the same thing but along x-axis. Okay, so let's say, okay, so these are the two formulas. So the equations that we're going to use is, the first equation will be the peak voltage, or sometimes it is known as amplitude. Amplitude is equal to gain, or sometimes y sensitivity, into x naught. And x naught will be in centimeter or number of divisions in height of the wave. The second formula will be for the time period, and the time period will be time base, or sometimes it is known as x sensitivity, that controls the movement along x-axis, into lambda. And again, lambda can be in centimeter or in divisions. So the third formula that you can use is frequency equal 1 over time period, because sometimes they can ask you to find the frequency of the wave. So you'll be using number 2 to find the time period, and then this time period should be in seconds. Like if it is in millisecond, you'll be converting into seconds, and then you'll be using 1 over t. That will give you the frequency of that wave. So that's how we're gonna plot or evaluate all the waves. Okay, so let me just quickly show you one example so that you can easily apply these 2 or 3 equations onto it. So what I'm going to do is I'm going to make a grid. 1, 2, 3. Usually 5 squares are there on the top and 5 at the bottom. 2, 3, and 4, 5. And in the similar way, 5 here. 1, 2, 3, 4, 5, and 1, 2, 3, and 4, 5. Okay. So now I'm gonna make the wave over there. So let me just carefully draw the wave like this. This. Okay, so the gain value here is 1.5 volt per centimeter, and this block is 1 centimeter, and along x-axis as well, this block is 1 centimeter, and the time base value is 20 millisecond, 20 millisecond per centimeter. What you have to do is you have to find the frequency of this wave, and you have to find the peak voltage, or they can ask you amplitude as well. But when they say amplitude, that will be in the volts. So you'll have to find this. So okay. Okay, so as you have found this V naught, so you know that V naught is gain into amplitude, and gain is given as 1.5 volt per centimeter, and 1, 2, 3, 4, 4 centimeters are there. Centimeter cancel away. So your peak voltage came to be 6.0. The sig fig are important over there. You have to write 6.0 because there are 2 sig fig over there. For the frequency, you know that you have to find time period first. So time period is time base into wavelength. Time base is given as 20 millisecond per centimeter, and wavelength you count 1, 2, 3, 4, 5, 6, 7, 8. So as you know, this is the wavelength. So in wavelength, 8 centimeters are there. So you just multiply them. So it is 160 millisecond. This is time period, but of course you have to find frequency. So you'll be using 1 over 160 into 10 raised power minus 3. So f is 10 to the minus 3 will be going up. So this will be this. So you can solve this to get your answer in hertz. Okay, moving forward, CR is done. So the next topic that we have to look is a very important topic, that is Doppler's effect. So Doppler effect is actually associated with variation in the frequency. It is associated with variation in frequency or wavelength of a wave, and that wave can be sound wave, or that waves can be electromagnetic waves such as light or radio or micro, any waves. So Doppler effect deals with variation in frequency or wavelength of a wave due to relative motion between source, which is producing source mean which is producing the wave, whether sound wave or electromagnetic wave, between source and observer. Observer is the one which is going to observe that wave. So this effect is very important. If I first tell you about its usefulness, so Doppler's effect, Doppler's usefulness is everywhere. It is used in medical field. You must have heard the echo test for heart, echo test for heart functioning. So that is also using Doppler effect. Then you must have seen the speed guns with the police at the highways, speed gun at highway. So that speed gun also uses the Doppler effect to measure the speed of the car. And then the next thing is radars, which tells you the position of the aeroplane, their speed or their position. This can be through Doppler effect. And the last but not the least is the universe expansion. We know that universe is expanding, and you must have studied that in your O levels in IGCSE, in the space physics, that universe is expanding and Big Bang and all that. So that was only possible because of the Doppler effect, that we can say that universe is expanding. So these are very, very important phenomena that are associated with Doppler. So let me first define the Doppler effect. What is Doppler effect? Before I define this, I can okay, but let me first write it and then I can tell you the example. Well, its definition is the variation in frequency of a wave due to relative motion between source and observer is known as Doppler effect. And this variation is apparent. The apparent variation. Apparent means that this is not permanent, but it is just observed when any one of them is moving. Either the source is moving or the observer is moving. Then the observer will hear the variation in the frequency of that sound. It's just similar to the thing that if a person is standing in the air and he is weighting himself, he's just going to measure his mass or weight. So that will be different. So let's say his weight comes out to be 900 Newton. And when the person is underwater, let's say the person is underwater. So if he measure his weight, then the weight should be, let's say, less than 900. Why? Because upthrust force is over there. Upthrust is there, but that weight is apparent. As soon as he gets out of the water, again his weight becomes 900. So the weight inside the water is apparent. Why? Because upthrust is over there. In the similar way, if a person is hearing a sound from a source that is at rest, so let's say this is a source which is producing a sound waves, and its frequency is fs. Let's say fs is the frequency of those sound waves, and let's say the sound waves are moving with the speed of v. So this v is the wave speed, the speed of sound, and fs is the frequency of sound at source. Like the source is producing the sound at this frequency, and let's say the observer is here. This is the observer, and these sound waves are going to reach the observer, and observer will hear the sound of frequency fo. Fo is called observed frequency, the one that he is getting, observed frequency. Okay, what happens is, if source is at rest and observer is at rest as well, neither of them is moving, then the observed frequency will be equal to source frequency, and there will be no change in frequency. So we say that observer will hear the normal sound. There will be no variation in the frequency of the sound. But the thing is, if we look upon the first case, case one is the one in which the source producing the wave is moving towards observer. So we say source moving towards observer. So what is going to happen when the source is moving towards the observer? So let's say this is the source and the observer is standing here. This is observer. Okay, the source is now producing the waves of frequency fs, and it is moving, sound wave is moving with v, and the source itself is moving with a speed of vs. S for source. So vs is the speed of the source and v is the speed of the sound. So this is sound speed. And okay, so when the source is moving, then what is going to happen is that all the waves will start compressing, over here near the observer. Why they start compressing near the observer? The thing is, okay, the thing is that when the source is moving towards the observer, then waves are going to be compressed over here, compressed waves. Why? Because he is producing waves and moving forward. So it means that every next wave will take less time to reach as compared to previous wave. Let's say if the source is here as one, he produces one wave, and then immediately reaches here and he produces the second wave. This is first wave, this is second wave. So of course the second wave will take less time to reach as compared to the first wave, because first wave is behind that. That's why all the waves are going to be compressed over there if the source is moving towards the observer. So what the observer will hear a frequency that is higher than the source frequency. Why higher? Because there are so many waves over there. As the waves are, less waves are going to be produced, but more waves are going to reach over there. So that's why the waves are compressed, too many waves. That's why the observed frequency is higher than the actual frequency. So if it is a sound, then the observer is going to hear a high-pitched sound. Why? We know that the pitch of the sound is proportional to frequency. This is the fact that we already know. So if the frequency increases, the pitch increases as well. So the observer is going to hear the high-pitched sound note. Okay, so it means that in this case, the observed frequency is not equal to source or actual frequency. In fact, the observed frequency will be higher than the source frequency. But if we have to find that, then there is a formula, and that formula is given in the formula sheet. And that formula is F naught is equal to V over V plus minus Vs into Fs. This is the formula which is given in the data booklet. Okay, this formula is given with a plus minus sign. You'll have to choose one sign for this case 1. So if in the case 1, you can see that the frequency is going to be higher. So for this case, the observed frequency will be V over V minus Vs into Fs. So this is the formula. Why I took minus? Because I want F naught to be higher than Fs. So for that, your V over V minus Vs should be more than 1. Because if the denominator is smaller, only then you will get a bigger number. So that's why if the source is moving towards observer, then you're going to use this equation with a negative sign over there. Okay. Sometimes they make the trick. They can ask you to tell the change in frequency, how much frequency changes. So you say, okay, no problem. Just use this F naught equation and subtract the actual wave. Fs is the actual wave frequency, and then you can tell that how much is the change in the frequency. So observed frequency minus actual frequency, you can find the change. So Fs is what? It is actual frequency. Okay, so this was case 1. Now let's move on to case 2. What is case 2? Case 2 is source moving away from observer. Source moving away from observer. Okay, so in this case, let's say if this is the source and the observer is here, so the source will be producing again the same sound waves, but the source is moving in opposite direction with the speed of Vs, and the sound waves are moving with the speed V. So now what is going to happen is that as the source is moving away, then less and less number of waves are going to reach the observer. Why? Because sound source is moving away. So it means that we can say waves expanded here. Unlike the other case in which it was compressed, over here waves are expanded. So now the observed frequency will be less than the actual frequency. So it means a low-pitched sound is heard. Low-pitched sound is heard. So it means that now if we use the formula, so that will be V over V plus Vs into Fs. So this is the formula that you are going to use if the source is moving away. Why? Because your observed frequency now is smaller than the actual frequency, and that can only happen if the denominator is bigger in value. If the denominator is bigger in value, of course, you can do that. You can show that the F naught is smaller than Fs. Okay, so these are the two cases for the Doppler effect which you'll have to use, and mostly the questions will be based on this. So let me quickly look for a question in which we can apply the Doppler effect. Yeah, so here is the question. This is the question. There is so much of the variety of Doppler effect, but let's just do one of it. The driver of the car in B sees a pedestrian standing directly ahead in the distance. The driver operates the horn of the car from time 15 to 17 seconds. The frequency of the sound heard by the pedestrian is 480. The speed of the sound in air is 340 meter per second. Use figure 2.2 to calculate the frequency of the sound emitted by the horn. Okay, so it means we'll have to go back. We'll have to look for the frequency. 2.2. Where is 2.2? Yeah, here is 2.2. Yeah. Okay, so the thing is that they're saying that from 15 to 17 seconds, he operated the horn. 15 to 17 seconds. So if you look here, where is 15 and where is 17? So here is 15 and 17 is, because this is 10 boxes, so each box represents 0.5. So 15.5, 16, if I just zoom in a bit more. So 15 is this, and then 16 is this, 17 is this, and this is 17.5. So it means this is the area in which he was producing the horn. So what was the speed of the car? We can, because here the speed is the 14. So you say that the speed of the source is 14 meter per second. So from this graph, we can see that what is the speed of the source? It is 14 meter per second. Okay, now let's move down to the question. Okay, so we say that speed of the source is 14 meter per second, and the speed of the sound, as they have already told us, the speed of the sound is 340 meter per second. And what frequency the pedestrian is heard? The frequency of the sound heard by the pedestrian is 480. So we say this is the observed frequency, which is 480 hertz. So they're saying that what is the frequency of sound emitted by the horn? So that is Fs, or the source frequency. You have to find that. Now the thing is, we know that the car is going to move through the pedestrian. Car is moving towards the pedestrian. So this is the case in which source moving towards observer. So as it is the case in which source is moving towards observer, so what we can do is we can say that, okay, we have to go to the formula sheet and we'll be looking at F naught is VFS over V minus VS. Why minus? Because when the source is moving towards, it is minus, because then F naught is obviously bigger than Fs. Okay, so now you have to find Fs. Your target is to find Fs. So what you'll be doing is you'll be making Fs as a subject. So shift this V minus Vs to the other side, so it will be F naught V minus Vs equal VFS. And then in the next step, shift V to the other side, so it is V F naught V minus Vs over V is equal to Fs. First do this, and then you put the values, all the values. So F naught is 480, which is observed by the observer. Okay, V is the wave speed, which is 340, minus Vs is the source speed, which is 14. And then down there V, which is the wave speed. So you will simply simplify this to get your answer. So this will be 326 over 340, and whatever answer will be coming, you'll be writing over there, keeping in mind the significant figure. In the question, the two significant figure is there, so you can write your answer in 2 or 3 significant figure. So that's how we can solve Doppler effect questions. Okay, I hope it is clear. So let's move to the next and the last thing in this, which is the polarization. Polarization of waves. Okay, what is polarization of waves? Polarization of wave is actually a phenomena in which we are going to restrict the oscillation of the wave. So if I simply write the definition, so I'll write process of restricting the oscillation of a wave along one axis or one plane is known as polarization. So it means that, let's say, in explanation of this, I can tell you that, let's say this is a light wave, and the light wave is oscillating usually in all directions. This is the oscillation of the light photon, which is happening in all the directions, all the possible directions. So what we're going to do is, we're going to restrict, this is how many axes? One axis, two axis, and three axis. So three, and then this is the fourth axis. So in four axes, they are moving. So what we do is, we want to restrict it to one axis. So what I'm going to use, let's say I'm going to use a blocker, which is like having, this is, let's say, a complete black paper, and then it is having only one narrow slit over there. So there's one narrow slit over there, and this is the gap, the white gap through which the light can pass. If it is made to fall on it, and then when it emerges it, only oscillation parallel to the gap is going to pass through it. All others are going to be blocked. So number 2 is blocked, number 3 is blocked, number 4 is blocked. Only this number 1, because it is parallel to this slit, is made to pass through it. So this wave is called polarized wave. This is polarized wave. And this slit that we have used, this is called polarized. This is polarized, or we say it is polarizing filter. Polarizing filter. And this whole process that just has happened, this whole process is known as polarization. Polarization. So polarization is actually a process of confining or restricting the oscillation of wave along one axis only, and for that we use polarizing filter. What is the everyday life example? It is widely used in everyday life. So first, it is used in car screens, front screens, in which it is used to remove the glare in night driving. Because when the headlights of the other sources make to fall on the screen, then there will be a lot of glare and the light will be spreading out. So the polarizing sheets are there installed already. They are built in the front screens that will remove the glare. And then your sunglasses. Now it's a summertime, so usually when people go out, they wear the sunglasses. Why they wear the sunglasses? Because they wanted to decrease the intensity of the light, because that will put a soothing effect on them, and they'll be comfortable while walking in the sunlight. So for that, polarizing filters are used on the glass of the on the glasses, right? So that process is also, like the polarization process is also happening over there. Okay, so after this, let me make a waveform. Let's say if there is a wave which is oscillating vertically. So let's say if it is only oscillating vertically, the wave is going like this. So this is a wave which is oscillating vertically. Okay, now we want to polarize it. So what we do is, we have a filter over there, and that filter is like this. We can place that filter in two positions. These are the two positions of the same filter. Maybe I should draw this again. Okay, you have to use these over there at this point. Like this is the point P. You have to use these one, like 1 and 2 over there. In one, what you'll be doing is that we will be using it like the way we have used it before, like this. And for the second one, as it is laid horizontally, so it will be like this. Like this. So this is called vertical position of the polarite, and this is called horizontal position of the polarite. So what happened is, if you fix number 1 over there, so what you are expecting at the output, like if I just remove this output over here, because you're placing it over there, so I have to remove this position from here. Okay, so let's say you are putting the polarite number 1 over there at P position, and you are placing it horizontally. So of course you will be getting the same wave as output. You will be getting the same wave. Why? Because this slit is also vertical and the wave is also moving vertically. So that's why all the wave will be passing through it. So we will say that when you place this, the whole wave passes. The whole wave passes. Okay, what about when you place number 2 over there? What is going to happen if you place number 2 over there? So let's say I'll again remove this, and now you are going to place the filter like it is in number 2. So when you place number 2 over there, then none of the wave will manage to pass through it. So it means you will see no wave here. So why you'll see no wave? Because the wave is moving vertically and your slit is horizontally. It means that we'll be saying no wave passes through it. So it means that we'll be saying that the whole of the wave is polarized. So one thing we can deduce from here, if the oscillation of the waves are parallel to the slit, they pass through it. But if the oscillations are at 90 degrees to the slit, then none of the wave will pass through it. So let's have a conclusion about it. So the first thing is, if theta is 0 between wave oscillation and slit, this is slit, no? This white one is called slit. So if this angle is 0, then we say that maximum or whole wave passes. Okay, what about number 2? Number 2 is if theta is 90 degree, and of course between wave oscillation and slit. So if the angle is 90 degree, then none of the wave passes. Then none of wave passes. It means the intensity becomes 0. I is the intensity. There is no intensity, complete blockage. And over here, the intensity will be maximum. Why? Because the wave is passing. Now, what about case number 3 now? Case number 3 is if theta is greater than 0, but less than 90, then what's going to happen? Then what will happen? How the intensity will change? So for that, we have to study a law that is called Malhuss's law. Malhuss's law. This is what we have to study for this. It is called Malhuss's law. Let me spell it correctly. Malhuss's law. So Malhuss's law actually tells us, the basic theme of this law is to discuss variation in emergent light intensity for different angles between polarizing filters and wave oscillation. Okay, so Okay, so yeah, our time is up. So maybe we'll be looking upon it in the next class tomorrow, inshallah. So tomorrow's class we'll be finishing this, and we will be doing electromagnetic waves. That's a shorter topic, and we will be starting the superposition as well. So tomorrow we'll be doing this, right?
Okay, sir. That's it.